this last section of the day entitled Interacting with Your 3D Geometry. You probably guessed I was a professional bodybuilder, but you're wrong. I'm actually a graphics software engineer with Intel. Okay. All right, so games, graphics, there's all sorts of fun stuff. You got particle systems, lens flares, cameras, lights. But any sort of meaningful interaction between the player and his environment happens with those geometric objects, whether it's rigid bodies, skin characters, or some of those soft body things that are becoming more and more important. And these all things, they all have meshes. Okay, so we're going to cover a wide variety of things today. I'm going to first cover a lot of basics, review for some people, but it's the fundamentals we want everybody to know. Following that, I'm going to dive deep into convex meshes. Then we'll take a look at solid meshes and spatial properties thereof that affect motion. And then we're going to finish off with some springy things. And hopefully lots of practical examples that'll be fun for you guys. And yeah, you're welcome to take pictures, of course, but these slides will be available online later on. Okay, this is math tutorial today. So you were warned there'd be some math in this course. But don't worry, a lot of it is very straightforward. In fact, just knowing your basic vector arithmetic, dot product, and cross product, that's going to give you guys 99% of what you need in this industry to succeed. For example, your standard lighting equations in your shaders on your GPU. I mean, it's n dot L, to get your diffuse lighting, just dot product. You're writing some game script code for, let's say, some robot, right? And you want to know, okay, if the player walks in front of you, you have to shoot him down. Well, simply take the dot product of the direction the robot is facing with the vector from the robot to the player, and if that vector's close to 1, he's in front, fire away. If it's negative, save your ammo, he's somewhere behind you, you don't see him. Okay, in addition to some of that basic math, there's going to be a few new things we're going to introduce today. Shown here on the right, the outer products and the Jacobians and stuff. You're probably wondering, outer product, what's that? Well, the dot product, or inner product, is something you're already familiar with. You can think of that as a row vector times a column vector, and that gives us the scalar we're all familiar with. The outer product, now think of it as a column vector times a row vector. The rules of matrix multiplication give you a 3 by 3 matrix. You're probably scratching your head wondering, okay, well, I started out with 6 numbers, I've got 9. That's like lossy compression where the result is bigger than the original file size. What's the point? Well, this is actually useful, and we'll see why. But first, let's take a look at sort of a geometric understanding of how the outer product might be used. Okay, we already know that what the dot product is. Let's say we have a vector that's of unit length, u. And we have some other vector, v, and we take the dot product. And that gives us this distance of v as if we projected along u. Now, that's a scalar. If we want, let's say, a vector along that line, then we multiply u dot v times u. And that gives us this line, so v projected onto that line. Okay. So now if we have u times u dot v, can we change the brackets and move it over to the left so it's u dot u times v? Well, that doesn't work, because that's just 1 times v, which is actually v, which is different than this projection vector that we wanted. So to do that, it's actually you take the outer product of u with itself, and that gives you a 3 by 3 matrix that if I multiply that matrix by any vector, it projects it onto that line. Okay. So think of how you might write your player navigation code. You got some guy running around your world, and the user hits the W key, and he's running along, and he hits a wall. And, well, you don't want him to go through the wall, but maybe you don't want to have him stick there. You want to have him maybe slide along the wall. So you've probably written a routine like this called slide along wall, where you take the intended velocity or vector of the user, v, and you have this u. Let's say this u vector is now sticking into the wall. And you subtract out that component of the motion, and you're left with the green arrow there, so the player's sliding along the wall. All right, so in that little equation, we see v show up in there twice. Can we factor that out? Well, indeed you can. And what you get is the identity matrix minus this outer product is now this 3 by 3 matrix that you can use to project vectors onto a plane, of which u is the normal of. Okay. Now, why it's sometimes useful to have things in that matrix form instead of just some function is, well, certain things you can pass matrices into, like other systems of equations and so on, where you can't necessarily stuff an arbitrary function. Okay. And we'll see more uses of this later on. Okay. Now, at first, because there's a lot of geometry algorithms that we're going to be writing, this is the bane of existence of these things, is numerical precision issues. If you're doing graphics and lighting, everything just kind of works out at, that pixel is always the right color. But, the problems are more when you're doing things with geometry like slicing and dicing and stuff. Now, it comes to this. When we have a line, for example, it's a continuous thing. And if you sort of zoom into like the lowest bits of precision, and you start looking at points along that line, well, they're not really on the line anymore because you don't quite have the precision to do that. And you're thinking, well, floating point, you got 23-bit mantissa, that should be more than enough precision. Well, the problem is still not enough because you might have a long line segment and you're chopping it, let's say, really close down to and making something really short. And as a result, you can sort of change the direction of that line a little bit and can throw things off. Or you have those two lines that are sort of like this. You saw examples in the previous talk. Or you might be doing successive operations and you get numerical drift and things get really bad. Okay. And we're going to see examples of this issue later on because it's just something that we have to be aware of. Okay. So geometries. Let's take a look at the building blocks. Now, triangles and planes. And your college math class probably taught you that a plane is a 2D subset of a 3D space. In games and graphics, of course, our planes and triangles have to specify an above and a below, or on top or in front, behind, whatever you like to call it. So for triangles, typically, there'll be a normal vector for the triangle saying which way is above, and maybe a counterclockwise convention to the vertices. For planes, it's that A, B, and C of the plane equation that define the normal which points up above. Okay. Also note that I prefer to use a convention ax plus by plus cz plus d equals 0, because then I can think of my plane-to-point test as this 4D dot product of the homogeneous coordinate or homogeneous point with the plane equation itself. One more small note. Often, instead of saying A, B, C, D, people will interchange and say X, Y, Z, W, because that's the same convention used for quaternions and homogeneous coordinates and float 4 registers and da-da-da-da-da. Okay. So now, one of the things that we're going to need to be able to do is, maybe find the intersection of 3 planes. Where do they all meet? You could have 3 faces on a mesh, and you want to know that vertex location. All right, well, this is a classic linear algebra problem of 3 equations and 3 unknowns. The x and y and z components of your position v are the unknowns. So take your 3 normals from the plane equations, put them in a 3 by 3 matrix, invert that, multiply it by this vector that composes the w coordinates, and voila, you get your answer. Now, if you have 2 planes that are parallel, well, that matrix won't be invertible, and there's no answer anyway. So all the math kind of nicely works out. Okay. All right. So what if we have 4 planes? Well, okay, I have to explain what I mean by this problem, and I'm going to do it with an example. Let's say I'm building a house. So I start with this floor, and I build up the walls, and then I'm constructing the roof. And before I'm done, I want to know, well, what's the top of that house going to look like? How do those 4 planes come together, just based on the plane equations? And there's 3 possibilities for that. I can have sort of the north-south come together first, or the east-west, or they might all actually meet at a point. Well, using what you just learned from a previous slide, you can think, oh, I'll grab 3 of the planes, generate a point, test it against the 4th plane. And yes, that will work. But one of the things that we like to do whenever we construct algorithms is, can we do it in such a way where we're not sort of, picking, how do I pick the 3, who's the odd man out, and so on. So instead of that, let's try putting all 4 plane equations now in a 4 by 4 matrix. Now, if they all do meet at a point, well, then I'll have a solution to the equation that's shown on this slide here. But I'm multiplying something by something else, and I'm getting 0. That's only going to happen if that matrix is singular. And we know a simple test for that already. And that's saying if the determinant of the matrix is 0. Furthermore, if my plane equations are in this matrix in a nice counterclockwise order, and I don't put any of my roofing material on upside down, then I can use the sign of the determinant to distinguish between the other 2 cases. Okay. Now, you've seen this, but I'm just going to ram it down your throat because everyone needs to know this. So sorry if it's review. But intersecting a line with a plane. I've got 2 points, and I want to know where they meet. V0 to V1 is my line segment. I can do that test, and I know the distance above and or below the plane. Okay. And so I think of now as I'm traveling from V0 to V1. Okay. Think of yourself moving that direction. And so it's a matter of just solving, at what time do I cross that plane? And shown on the right, that's high school math to find that value of t, or for time. So once you've got that, then you take that value, shove it back in your equation, sort of move along that line, t, that fraction t, and you've got your 3D point of impact. Okay. All right. So getting back to doing some interaction in a game, well, things are made of triangles. So if let's say the user clicks on his mouse, and you want to know, well, what did he click on? Or you've got some bullet flying through the scene, and does it hit the bad guy? So yeah, here we have to test this ray, the path of the bullet, against our geometry, say a triangle. So the triangle sits on a plane. We find the point on the plane where it hits, and then we say, well, we want to know if it's inside or out, so we test against all of the edges. Okay, this is the simple, easy, simplistic way of doing it. And in order to test against an edge, you have the edge cross product with the, from one of the edge vertices to that point, and if that cross product vector points the same direction as the normal, then yeah, it's on the inside of that edge. On the inside of all three edges, you hit the triangle. Outside any of the edges, obviously you missed. Okay, right, and that's sort of the simple first implementation that you might write and implement. Okay, but things in your game, they have like thousands of triangles on them. Well, the answer's simple. Just check against all of the triangles. Now, okay, that's obviously going to be fairly inefficient, and I invite you all tomorrow to attend Gino's talk on spatial structures, because he'll tell you how to rule out many of those tests altogether. Okay, but just conceptually for now, you can sort of think of it that way. But also keep in mind, depending on how you traverse those spatial structures and what's in your scene, if you detect a hit, ooh, I got a triangle, well, you might have to keep checking, because there might be something closer, right, that hit. So as you're checking, you sort of shorten your ray and keep going, because you don't want to spray like a bunch of bullets against the crowd and have the people in the back fall down. No, you want the zombies in the front to fall down. Okay. Next, here's an issue you need to be aware of, is I can have two triangles, nicely sitting together, and I shoot a ray, and ooh, it goes right through. But the same edge, they got the same points. And that's because of this naive implementation. When I'm checking against one triangle, I generate a point on that plane, and let's say, numerical precision just falls outside an edge. Check the other triangle, well, I'm projecting onto a different plane, so I'm generating a different point. Okay? And so, you have to kind of be aware of this. I mean, a simple fix would be to kind of make the triangles a little bigger or something. Or, you can go back and study Gino's slides and, with Plucker coordinates and do this all the correct way. Now, and finally, your meshes themselves, well, they have to be intact. If you've got T intersections that are holes, you can imagine a bullet flying right through where there's a missing triangle. And that brings us to this notion of solid geometry. And we touched on that a little bit in the last section. You saw that. And that's this idea where you have a borderless manifold mesh. So anytime you have an edge, there's a face on both sides. And the normals are sort of all consistently facing outward and so on. And then it's all watertight. Nothing could leak in or out. And so the mesh itself becomes this infinitely thin boundary representation separating solid matter from empty space. Okay. And then, given that, I can take a point, and I can say whether that point definitively is inside or outside of my mesh. Just simply cast a long ray. If you first hit the backside of a polygon, it has to be on the inside of the object. Otherwise, it's free in the clear in empty space outside. Okay. All right. So that's a little bit of review for everyone. Now I'm going to dive deep into convex meshes. Okay. Now, your university classes or textbooks might have described a convex set is one for which any two elements, if you have picked any two elements in that set, the line segment between them must also be contained in that set. Okay. Now, more intuitive ways to understand a convex mesh is to think anytime you've got two neighboring faces, their normals are going to be tilting away from each other instead of towards each other. A test for that, you take the cross product of triangle face A with face B, and the result should run in the same direction as the edge according to face A. You can also think of a convex mesh as a volume bounded by a number of planes, the intersection of a number of half spaces, essentially. Or you can think of every vertex lies at or below every other face. Okay. So the reason for convex meshes is that a lot of algorithms become so much easier to implement. Okay. For example, an in and out test. Well, to test if a point's inside a convex mesh, I just have to check with all the plane equations. If you're underneath all the planes, you're inside. I don't have to worry about those edge tests and corner cases, numeric robustness, and all that. So that gets a little easier. Testing a ray, like that bullet flying through space, whatever. For a ray intersecting a convex, well, so I've got that ray, and then I've got this thing made out of planes, and just for whenever I take all the planes that are facing against the ray, so like the dot product of the ray and that plane normal is less than 0, and then it's just cropping any part of the ray that lies above, right? So here I'm sort of moving the back start of the ray, this V0, moving it up, as it's being chopped by each of these planes. And then if I'm left with something of positive length, then that V0 is now the point of impact. The last plane that sliced it is the normal of impact. And this generalizes, of course, to a general line segment with two endpoints. And just sort of, in addition to trimming, from V0 with the front-facing planes, I trim V1 with sort of the back-facing planes. And if I'm left with something of positive length at the end, then that's what's stuck inside my object. All right. So convex to convexes. Well, there's a nice property here that if two convex objects are not interpenetrating, there'll be a separating plane between them. And I'm sure the physics sessions tomorrow, if you attend those, they'll tell you all about fast ways to find these. Furthermore, if they are separated, one of the planes that will separate the two will be either a face from one, a face from the other, or something that takes an edge from each, and the cross product is its normal. Okay. Learn more about that tomorrow, I'm sure. If two convexes are touching, then the area, or contact patch which they're touching, will be either a point, a line segment, or itself a convex polygon. So you can understand why physics engines really like these things. Okay. So I've sold you that, hey, convexes are cool. We want to use these for a lot of reasons. But I've got things in my scene, and oh, they're not convex. What do I do? Well, in that case, you generate a Convex Hull for those meshes, which is simply the smallest convex mesh that contains the original mesh. Well, so how do you do that? This is something that people have been doing for like 40 years now. And there's two general categories of approaches for generating convex hulls. You can start with like a big bounding box, and you kind of shrink it down and slice it, chop it, whatever, until you get something that tightly fits all your points. Or you can start really small with like, maybe a couple of back-to-back triangles or tetrahedron, something convex, and then you add points to it, keeping it convex as you grow it out until you've grown it out to contain all your points. Okay. So the most popular implementation out there is Q-Hull, based on the Quick Hull paper, and it's one of these expansionist types of algorithms. It works in an arbitrary number of dimensions, but typically if you're going to use it, you're going to use it for three-dimensional things. And it's one of these expansionist approaches. And so I've just illustrated what that looks like on the right. I've got some convex mesh, and there's a new point that we're going to add. Find all the faces for which it's above. Okay, then you throw those away, and there's left with the silhouette, and then you fill that hole with a new fan of polygons. An issue is you get, and then just continue for the next vertex and so on until you've grown it up as big as you want. But at each step, you have this issue where you have to make sure that things are still intact and convex. And even the original Quick Hull paper says, yeah, we have these numerical robustness issues. They always show up. You just have to constantly scan for them and fix them when you see them. What that might look like is as follows. Here I've got some little hull, and I grow it with this new yellow point out here. Throw away a couple triangles, and I add these three. And notice that one of them is kind of skinny. And so you can see where, if something's skinny like that, the normal might be bent over in a weird way, and it might not be convex. And so maybe flipping an edge or something will fix that sort of thing. Okay. And these algorithms typically work with winged edge data structures, which are very effective for this. But there's also a simple approach for Hull generation, just based on triangle meshes. It also works. And that's to think of, again, this is one of these expansion approaches. So you have this triangulated mesh, and anytime I want to iteratively grow the hull with new points, I find all the triangles for which it's above, then I take a tetrahedron and I glue it on top. Okay. So where the three of the points are the three vertices of the triangle that I'm putting it on top of, and the fourth point is my new point up here. And then, because we don't want all this stuff inside, we sort of just delete all the back-to-back triangles, and I'm left with just the boundary representation on the outside. So, fairly simple, fairly elegant. But it too runs into this numerical robustness problem, because you can generate the folds and stuff even with this approach. So I'm going to sort of dive into an example here to illustrate how they happen and how to fix them. So imagine I've got some point cloud and a bunch of vertices that I'm generating a convex hull for. And 5 of these points, A, B, C, D, E, are at one end of this cloud, and they're all sort of coplanar-ish. And at some point, I've generated an intermediate hull that's got all the points except for E. And now we want to add E to our hull for whatever reason. And OK, so I test E with the left triangle, and using 6-bit mathematics, it tells me that it's below. Okay. And then I test with the right triangle, and bad numerical precision, and it tells me, oh yeah, you're above that triangle. So then I have to slap a tetrahedron on top of the right triangle, lift it up, and this new vertex is over to E. Well, look what happened. I've got this upside-down red triangle that's facing the wrong way. So as long as I have one point that's inside my convex hull, I can test for these and detect them. The solution is as simple as the way we're generating these hulls. You just take a new tetrahedron and you shove it in there. What it does, it deletes the bad triangle and the one that we didn't lift up in the first place, generates the two green triangles shown on the far right, and I'm left with this nice convex hull, everything facing outward as we like. Okay. And that's how that works. All right. So a lot of the off-the-shelf convex hull algorithms out there are going to generate your complete hull with all points on the extreme. But you may not really need all of those. Imagine if you've got a whole bunch of points in a point cloud, and there's sort of this round feature on the side. All of those, every single one of those points, if they're extreme hull, are going to be included. The thing is, a convex hull is already this gross approximation, right? I mean, you don't need that many points. Maybe 30 will probably be more than enough. So the quick hull algorithm, it's order n log n time, and that's the contribution of the paper. One of the reasons that it is that way is because of the way they sort of order vertices to add to the hull. So instead of that, we don't really care about order n log n because this is offline processing typically. We're just kind of preparing our stuff to use at runtime. This isn't at runtime. But let's instead, at each step, let's always pick the best vertex. So we're always picking the best one to increase our volume of our hull the most. And then we can just stop if adding new vertices doesn't improve it, or if we've kind of reached a threshold, we don't want any more vertices than that. Okay. So that's the way to make your stuff game efficient. Okay. Furthermore, there's this trade-off between minimizing the number of planes versus minimizing the number of points. And what I've shown up here is two platonic solids that illustrate this trade-off perfectly. One has fewer planes, one has fewer points. Now, the algorithms I described for creating simplified hull work on vertices, and they're triangulated. But if you can use what's known as a geometric dual to solve for the other one. And I'll just sort of leave it as an exercise to look that up and study it, because I don't have a whole lot of time to get into it in a lot of detail. But essentially, by taking the dual, and so I have all these points that are actually the plane equations from this original full hull. When you compute a simplified hull that minimizes vertices, you're actually minimizing planes. Take the dual back, and you've got a hull that will look more like the one on the right. Vertices will typically have a valence of 3, and faces will have 5 or 6 sides, as opposed to something that looks triangulated. There's a trade-off. Sometimes you want fewer vertices if it's something like you're doing GJK a lot. Sometimes if you're doing like a lot of plane tests, then you want to have fewer planes. So there's trade-offs for which is better. All right. Okay, so you know how to generate convex hulls, but let's say I've got some objects that it's not realistic enough. And things are colliding in the air, and it just doesn't look right. The fidelity is missing. So the solution there is to take more complicated objects and break them down into convex parts so you get a tighter fit. And artists can do this in 3ds Max or Maya. But fortunately, that could be a bit of work. Fortunately, there's a couple tools out there that can help. John Ratcliffe on the PhysX team now at NVIDIA, and Khaled Mamou, who now works at AMD. Both of these guys have written software. It's open source, free to download and use, that you can throw in your game engine. It'll do exactly this for you. Alternatively, if you've got skin characters, well, you've already kind of done the work, because it's rigged. You've got bones. You can grab for all the bones, simply sample your skin mesh, find any vertices that are weighted to that bone, and generate a hull or collision volume based on that. Okay. So an example of that is shown here. And okay, I mean, you've all seen ragdolls falling downstairs demos and that sort of thing. So here, you see that's the skin mesh that we're drawing and showing. Okay. But instead of the actual skin mesh doing the interaction, it's really the underlying bones that are doing all the collision detection and interacting in the scene. Okay, so that would be the way to do it, and not just characters like full body, but other types of objects as well. You would do the same sort of thing. And there's our ragdoll hand, for example. Okay. Next, we're gonna take a little detour and take a look at Boolean operations. Another fun subject in computational solid geometry. So this is when you have a mesh, remember they're solid, they define sort of empty and solid space. And if I have 2 of them, I can do set operations: union, intersection, and subtraction. A couple examples are shown in this video. Now in the general case, you want to have a good winged edge data structure to implement this. And what you would do is you would take all the edges of one, slice them with all the faces of the other, and vice versa. And then whenever one passes in or out of the other, you have to sort of tessellate along it, adding new edges, and for the other one as well. And then match those edges, and then sort of take half of one, half of the other, stick them together, you got your Boolean operation. Okay. Now, what I described in a few sentences is actually a heck of a lot harder to implement. You've got all those corner cases, numeric robustness, tolerance issues. It's not easy. So let's take a step back and think, okay, where are we going to use this stuff? Certainly level design, modeling, there's applications there. But a lot of the R tools, they already have this stuff built in. So if you're thinking at runtime, well, hey, destruction is kind of fun, or geomod where I'm tunneling through some environments and that. But in these cases, I don't have an artist who's like finely tweaking and placing points. No, I'm like chucking grenades and blowing stuff up. So, you might be thinking, okay, is there like a quick and dirty, simple approach? Maybe something based on convexes, since we've been looking at those recently. And sure, okay, let's explore that a little bit. So we've already seen, mesh cropping or slicing, where we, chopping all the edges. If you crop a convex mesh, you have this nice property that there's, you get an open loop, okay, but there's only going to be one. Okay, in general mesh, you can get more. But then that loop is also going to be a convex polygon, so it'll be easy to triangulate when you get to that step for rendering. So intersecting two convexes, you can think of it as cropping one with all the planes of the other. Okay, but wait a sec. You saw I took a convex mesh earlier and another convex mesh, and I subtracted one from the other, and the result wasn't convex. How does that work? Well, that's because, that was a subtraction, not an intersection. The subtraction with the solid is the same as doing an intersection with all the stuff around it. So you can do non-convex operands as a union of all these, of a bunch of convex operands. So you basically do all those convex to convex intersections and then just, throw the result together. Okay. All right. But even we saw Convex Hull, chopping a line. Even chopping a convex object, you're subject to those annoying numerical robustness issues. You can do things like, check the planes, make sure, you're not generating any sort of twist, because if you have a plane that's coming very close to a vertex, if you make a mistake and you sort of, chop these edges instead of those ones, you can generate little problems at the corners. And then it still gets more hairy because, you might have more than 4 planes. You might have like 5 or 6. And so you're probably thinking, oh, there's too many corner cases. Is there something simple I can do, like a snap to grid or something, and just not have to deal with any of this stuff? Okay, so here's a little trick that I've been doing for geomod for a while that it kind of works. And that's not snap to grid, but it's something a little different. It's quantize the plane equations. So any of the Boolean operands will only have plane equations that satisfy certain conditions. And what it is I take remember our plane equations are ax plus b, y plus c, z plus d equals 0. If I multiply those numbers by some number, it's still the same plane. So I make sure for any of the plane equations, there exists some number I can multiply it by so that a, b, c, d are all integers. Furthermore, a, b, and c are integers less than a small constant. All right. So now recall how when I have a vertex, it's going to be the intersection of 3 or more planes. And how did we compute that? Well, we had this matrix, right? And that M matrix there of the normals, that's all integer values now. I invert it and multiply it by this vector, which are all integer values now. And so the result is going to be this point V, of which its x, y, and z components are all going to be rational numbers, where the denominator is no larger than the determinant. Because when I take an inverse of matrix, I have to divide by the determinant. So that means for any 2 points I generate, if they're not the same point, they'll have to be at least one over that determinant distance apart from each other. Well, what this gives me is a hard-coded fixed epsilon I can throw in my code, to tell me whether 2 points are the same or not. Okay. And based on that, I can throw rocks at this piece of glass all day, and nothing is ever going to break. Well, the glass is going to break, but the code isn't. Okay. So now, even though it's doing this, there's no integer math in the implementation. No. All that stuff you saw on the last slide, that was just proof that this works. The implementation itself is, floating point math, 32-bit, don't need double precision. Normals are of unit length, just as you'd like. But the code itself doesn't have all those fancy, all those crazy corner cases, if then else statements, and this and that. So although here it's running on just a single core CPU, I mean, it potentially could run on a GPU fairly easily, like GPU type of implementation. And it's fairly efficient. I can do many Boolean operations per frame, break lots of glass. I can take the part that I chunk out, and I can generate little pieces of fragments or extra rigid bodies from them. Okay. So hey, that number theory course I took in university was actually useful for something. Okay. Next, we're going to take a look at some of the spatial properties of our solid objects. So when we have these meshes and they're solid, again, I'm stressing that's an important factor, we can correctly calculate the volume, center mass, and the inertia of our objects, which will affect motions, we'll see. Okay. So I'm going to cover a little bit of review material or introductory material, depending on your perspective. Okay, so the center of mass of a triangle. Now, there's many ways to define center, but this is the center of mass. So if I chuck the triangle up in the air, what point is it going to spin around? That happens to be the point where if I take the 3 vertices and divide by 3, that's that point. Okay. The area of a triangle, well, if I take 2 edges, take the cross product, figure out its magnitude, half of that is going to be the triangle area. Now, if I have a triangle with a predefined normal, well then instead of taking the magnitude, I can just take the dot product with that normal. An advantage here is I actually get a signed area, so I could have triangles in negative area, and soon we will see why that's useful. Okay. Okay. Now, just to make it clear to everyone, it doesn't matter which 2 edges you pick. When you take the cross product, you're going to get the exact same result, unless you're going the other way, and then you'll get the negative result. Okay. So how do I get the area of a polygon, something with endpoints? Well, break it down into a bunch of triangles. Find some reference point P, could be the origin, doesn't matter. And for every edge on my polygon, take those 2 vertices, my reference point, that's a triangle, and just add all those areas together. But what if this point P is on the outside of my polygon? Or if my polygon is all sorts of concavities and stuff, it's not convex. It doesn't matter, this still works. Because, sure, I'm covering a bunch of area that's on the outside, so but I'm also going to be adding these negative area triangles. It's going to cancel all that out. So you get the same result. It just works. Okay. Oh, here, okay, so here, if I've got a tetrahedron, and now if I take the cross product from all 4 of the sides and combine them together, they cancel each other out. Okay? So add these 4 vectors, and the result is 0. Now, remember how we generated those convex hulls with slapping the tetrahedrons together and then removing the back-to-back triangles, which obviously those 2 normals would cancel out. So by mathematical induction, you can conclude that for any mesh that's closed and solid, adding up all the area-weighted normals is going to add up to 0. And that lets us and that's why this works. Okay. Generating the polygon, the normal of a polygon with endpoints, and this could be a polygon. I shouldn't have drawn a convex one because it could not actually work with something that's concave and points slightly off the plane equation and stuff. It's a matter of adding up combining all the triangle normals with the same sort of triangle summation. Not the magnitudes, but taking those vectors, combining them together, and getting this long green vector shown on the bottom right. That is the normal of the polygon, and length is double the area. Okay. And again, if this point P lies on further away, sure, those arrows are going to grow on top because there's more area, but there's also negative things pointing down that sort of cancel each other out. The reference point P doesn't even have to lie on the same plane as all the other points. The only way it's going to break down is that if P is so far away that you're going to run into rounding error. Okay. All right, so that's the 2D stuff. Now let's start looking at the 3D things. You may have guessed that the center of mass of a tetrahedron is the average of the 4 vertices. And volume. Okay, well, that's sort of base times height. Let's think of that. The base area is, we have that cross product, which conveniently gives us this vector that points straight up. Okay, so half of that. Now, in this vector form, we can take as our, instead of, because we don't know the height per se, but we can take any edge leading up to our 4th vertex and dot product with that, because only this orthogonal component is going to matter, and that will give us our volume. But it's actually 1/3 because it's a pyramid. Okay, so this cross dot combo is also known as the triple product, and as mentioned in an earlier talk, it is mathematically equivalent to taking those three vectors, the three edges from this tetrahedron, shoving them in a matrix and taking the determinant. Okay. All right. So whatever we can deduce through simple geometric reasoning, we can also solve through very complicated calculus. So what I've shown here at the top is this is the definite integral, where the limits of the integration describe the limits or the region of the tetrahedron. And I can pass any function I want into there. So if I take my unit function, I pass it in and run off for a few days and write out all this calculus and make sure I'm right, I will come back with the formula for the volume. If I pass in a function that basically returns the position, adjusted for volume, then I get back my center of mass. Okay. Now I'm going to invoke this a little bit later. I just want to take the opportunity now to scare everybody with it. Okay. So, all right, you don't have a whole lot of four-sided, four-poly objects in your game. You probably have like tens of thousands of triangles on your objects. So how do you get the volume of them? Well, now, just like we saw a triangle summation, what we do here is tetrahedral summation. For all the triangles, the 3 points, plus some reference point, perhaps the origin, we just add up all these tetrahedral volumes, and that gives us the volume of our entire object. And again, the same principle of things falling on the outside and negative volume tetrahedrons canceling out, it all just works. Center of mass, well, as you'd expect, it's just a volume-weighted average of all the center of masses of all the little tetrahedrons. Okay, so getting the right center of mass is a good thing to do. So here we have this catapult arm sort of thing, and it's got we throw it in a physics scene, rig it up with a hinge joint, and there's sort of this large volume at the other end of the handle. So the center of mass, if we calculate it right, it's going to be somewhere around there. And then we just kind of let it fly in a game environment. We kind of get this nice behavior that we'd expect. Now, we didn't have to write any custom code. There's no springs here. This is just emergent behavior, the way that we like to enable artists to build things. Had I taken the bounding box of this object and taken its center and used that as a center of mass, we wouldn't have had this kind of behavior. Okay, so having solid meshes and solid matter matters. Okay. All right, so the third aspect of spatial properties that affects motion is the inertia. Hopefully everyone's familiar with the moment of inertia in 2D. And you have this idea that if you've got something spinning, something orbiting around a fixed axis, then for stuff that's further away from that axis, it takes a little bit more energy to get it up to speed. Okay. So I've rewritten this moment of inertia calculation in a couple ways here, so you can try to understand it as, it's sort of the variance along x plus the variance along y to give you the moment of something spinning around z. Because when we step up to 3 dimensions, it's not a scalar anymore. We have a 3x3 matrix known as the inertia tensor that describes the motion of an object. And the form of that's shown in the bottom right. And then there's a high relationship between this matrix and the covariance matrix. So in order to compute inertia, we're actually going to compute covariance. Because with one, you have the other, and vice versa. Okay. So if you studied statistics, this might look familiar to you. If not, it's still pretty easy. Imagine if I have an object that consists of a number of discrete little point masses. Okay. To compute its covariance, it's simply summing up the outer product of all those positions with themselves in a matrix. Okay. So yes, here's yet another use of that outer product that I mentioned in the beginning. Okay. So all right, that gives me the covariance of something with a bunch of points, but our objects are these continuous solids. So what we're going to try to do is one of those tetrahedral summation tricks. So now if I just get the covariance contribution from a single tetrahedron, then I'm done. So what I'm going to re-invoke that scary triple integral, but I'm going to shove inside of it that outer product. Okay. And I did this online on Wolfram Alpha, where I'd shove in the equation, but then it timed out on me. So I had to put in part of the equation and then get half the result and then shove in the rest. Because the free version online just doesn't give you enough free cycles or something. But you have to trust me that the answer at the bottom there is the right. So now I know this calculus might go over the heads of some people. Don't worry about it. What we have now is a formula for getting the covariance contribution from a single tetrahedron. And then, remember, we wanted to get the inertia. And so we have this covariance, and I've rewritten in the middle line there is in another form because it's a 3 by 3 matrix. So each of the ij elements of that matrix looks exactly like this. And we're summing over the mesh where u, v, and w are sort of the 3 vertices of each triangle. But because we know things will spin about their center of mass, we can't use any reference point. We have to use the center of mass as we do this summation. Okay, so let's say, we got covariance, and then to get to inertia, it's that formula that's shown at the bottom. Or if you look at the top left, we see the y plus zz in the upper left-hand corner of the inertia matrix. That's because, if you're spinning around x, it's the stuff along x that doesn't matter. It's sort of the other two, and that, the relationship between the two. But the matrices, covariance, the inertia, they have the same eigenvectors. They diagonalize the same, so it's all good. So anyway, enough of that. We've got our inertia matrix. So let's, how do we use this? And what the inertia is it defines a relationship between angular momentum and angular spin. But spin also depends on the current orientation. So here we've got some spinning objects. They're all the same object. They have the same angular momentum, but the spin is very different because they started at different orientations. So you can see some things are going to be spinning a little faster because they're going around, sort of the long axis versus the short axis, right? Even though they have the same momentum. So as we knock these things around, we sort of get the behavior, the way things process and all that stuff. Now, there's no gravity, but hopefully as we hit things, it takes less energy to get them sort of spin sort of the short way versus the long way and stuff. Here I've added gravity back in, but apparently not a whole lot of gravity, so this looks like, kind of in slow motion, like, got a GoPro camera and you're like filming your skateboarding tricks or something. But hopefully the behavior looks, this is kind of what you'd expect. You could do kickflips in an environment like this. Landed it, perfect. Okay. Oh yeah, and the equation is sort of shown on the right there. And you probably notice also that the spin vector sort of changes. It's the momentum that stays constant, but the spin actually changes from frame to frame. Okay. So what we looked at so far was the volume integration, or calculating these properties of our objects. So now, that's sort of the work half. Let's study the other half, the fun half, a little bit more, and that's this time integration. Okay, so volume integration and then now time integration. Well, that's just fancy terminology for how you update some objects from its current state to where it is at the next time step. So for position, you've got some guy, position pt at time t. His position at pt plus delta t is simply you add his velocity times the time step, and you got the new position. So, okay, this morning you took a class about quaternions, and you're thinking, hey, I've got a spin vector. I know how to create a quaternion from that based on the spin, and so I can multiply that pre-multiply that quaternion by my orientation to get my new orientation. And yeah, that sort of works. But one of the things, and we'll see why in a minute, is that what we'd like to do is form these time integration equations as adding instead of multiplication. So the form on the right here is where I've got my next state, my next orientation, is my current quaternion, current orientation, plus this derivative, plus a derivative, i.e. how that quaternion is going to change, times the time step value, like how much I'm going to change, or how much time has elapsed. Okay. So it gets a little trickier. Another important thing is that, remember that spin vector we saw that was sort of changing? The thing is, when I'm doing this orientation update, and this is the problem, that it's only valid at the beginning of the time step. So I can't really apply that same vector, that same spin for the entire time step. You get this thing called numerical drift, and it's best explained by the classic example of you're following the path of a circle. So say I'm following the path of a circle. What I would do is I would look down. What's the tangent? Take a step. Okay. Look down. What's the tangent or the derivative? Take another step, and so on. But if I'm taking big steps, shown in the little picture there in the upper right, I'm going to be slightly, getting further away from the origin or falling out of orbit. Okay, and that's what happens with the typical what's known as a forward Euler update. You sort of take that derivative from the current time step and you apply delta t time to that. So now instead, let's say I'm going to use a different approach to follow the path of a circle. Okay, using this Runge-Kutta technique. what you do is, okay, you look down at the circle, you say, what's the tangent? Okay, then instead of taking a full step using that along that tangent, you sort of look half a step forward in that direction, look down, what's the tangent at that point, or the derivative at that point? Ah, okay, now you've got a new derivative. Lean back, take a half step along that direction, look down, what's the tangent or derivative here? Okay, got an instant value, lean back. Now lean sort of forward a full step with that latest tangent vector, look down, okay, what's the derivative or tangent out here? And then, instead of using that last one, you take actually this weighted average of all 4 of those derivatives, or all 4 of those tangents, and that's how you advance yourself. Okay? And this works great for people who like to walk around in circles, and it's a perfect way to update our orientation in our games. So first, I'm going to show objects with a very high angular momentum, okay, and I'm going to turn on that forward Euler update, and look what happens. Okay, my object gained a whole bunch of energy, and the spin sort of converged to one of the principal axes of the object. Here I'm doing that Runge-Kutta update, and it's not gaining energy. This just kind of works. It's sort of spinning, gaining that nice behavior as we'd expect, and the spin sort of orbits around the momentum, which is what this shape of object is going to give us. Okay. All right. So we've looked so far sort of at rigid body objects and how they kind of work. Now we're going to explore the soft stuff a little bit. Okay. So instead of an object with a position and an orientation, don't worry about orientation, but every vertex on the object has its own position now. But all these vertices are going to sort of be connected with some sort of constraint or spring. Okay. And okay, so when we build these sorts of things, there will be a visual mesh for our objects, but the way we connect them with these springs or constraints might actually differ from that. Cloth is a classic example, so let's take a look at how we build like a cloth mesh for simulation. You've got a whole bunch of vertices or points, and you're going to create these strong connections with their immediate neighbors, because cloth doesn't really stretch or compress all that much along that dimension. And then, okay, there's going to be some sort of, do an example here if this works. You're going to, it might shear a little bit like this, but there'll be some resistance to it. So for every vertex, along the diagonals, you're going to create some sort of connection with maybe a slightly less stiff connection between them. And to resist bending, something bending over like this, you have connections between every vertex and 2 over in each direction. Okay, and you'd have like stiffer connections for something like leather, or for something like silk. They'd be very weak or non-existent. Okay. And it's not just cloth. I mean, you can build like rubber ducks or things out of 3D lattices of all sorts of connections. Okay, so for implementing these, it really comes down to the time integration. How do you simulate these soft objects? And there's 2 schools of thought. There's the kinematic approach and the dynamic approach. Now, the kinematic approach is to think of, any time I have a connection between 2 vertices, that's a constraint. Those 2 things belong at this, this distance apart from each other. And so for the implementation, every frame, you'll see if 2 points, if they're further away than they need to be, then you sort of nudge them closer. Maybe not move them all the way, maybe you nudge them a little bit closer, maybe do a few passes or something like that. Or if they're too close, then you just kind of nudge them apart. So it's very easy to implement, just your basic vector arithmetic that I'm sure everyone's familiar with. Plus you also have to know how to take a square root, assuming you can do that too. Then you can implement this. And you can find many reference implementations and papers on how to do it. A nice thing is that these systems, they don't explode, because you're always pushing stuff closer to where it's supposed to be. You're not going to get any weird behavior where things all of a sudden vaporize and go off in space. And not surprisingly, it's the most common system used out there in games and physics engines. The only caveat is that because the way you're sort of implementing, if you have things that are under sort of a true stress, either compression or stretch, are they guaranteed to converge to some sort of force-correct state? I'm sure there's implementations where people have figured out how to do that, but the alternative is to use a dynamic approach to solving cloth. And this is the pure physics approach. And it's to think whenever I have two vertices that are connected, they're connected with a spring that applies force. Okay. So if I've got springs that are fairly weak in force, it's easy to implement. You just sort of add a little velocity to each of those endpoints, and it moves and so on. But if I have, let's say, a very, very stiff spring, And let's say because a character in a game kind of moves one endpoint or something, now I have this string that's stretched out. And if it's a very high force and I want to simulate that, even if it's only 1/60th of a second, I can bang to pull it back together, but it'll overshoot because the forces are so high. And then it's like, oh, now it's even more out of whack, and then it shoots, and then boom, boom, and these things just explode, right? So even if you try to run kata integration, well, you're sort of looking at half steps, but I mean half of a huge number is still a pretty huge number, so that doesn't work. The only way to actually integrate these properly is with implicit integration or backward Euler. And we're going to take a look at that. But first, let's compare with the kinematic approach. Now, it's easy to implement. You can have this is actually running on a single core, lots of cloth. It's easy to do. Now, excuse my shading. It might look a little plasticky, but hopefully you look at this, think, yeah, that behavior works. Fairly responsive. I could use this in a game, and yeah, it kind of does the job. And chances are this probably is good enough for most people. The only caveat, as I mentioned, is I'm sort of pulling on things. I have all these constraints that are sort of fighting against each other, and the way these things are connected, you can kind of get this continued oscillation because you're not sort of, it's not getting to this relaxed, forced converged state. It's no, you're constantly fighting. So that's the only case where these things may break down. It might depend on the implementation too. So we're going to now take a look at sort of the implicit integration approach because it's kind of interesting. You might actually learn something. And like I said, it's based on forces and springs. And the forward Euler approach is as follows. You have, for every point in your cloth or soft object, it's got a velocity, and then all these springs connected to it, and gravity and wind or whatever else. So at each point, there's a net force being applied to a point or a vertex. So the forward Euler update would be to, divide that net force by your mass, which is your acceleration, apply that, and you got your velocity for the next time step. Okay, we've already described why that's going to break down because things might explode. So the implicit approach, what you do is instead of applying the forces at a point based on the forces at the start of the time step, you use the forces from the end of the time step. But wait a second, those are forces from the future. We're not there yet. We don't know what they are because we don't know where everything's going to be. I mean, how can we even do that? And so that's why for this approach, you end up creating one of these linear systems and solving for those forces. And in order to do that, you need to know the derivatives of the forces. That is, how the force at a point will change based on a change in position and a change in velocity. Okay. So now, the thing is with force in springs in a 3D world, is a 3D vector. And I can move something. As I move a spring, I can move that point in 3D. So the derivative is this 3x3 matrix known as a Jacobian. And the general form is shown in the upper right. So that's what we would have to derive to implement these systems. Now, we don't have a whole lot of time left to go deep into a whole bunch of calculus, but fortunately we don't have to. Let's try some geometric intuition instead. When I have a spring, it's a simple, kind of a linear thing. So let's first look at how does the force change, this derivative of force, along the spring direction. Well, if I have a spring, and let's say one point's at the origin and the other point's at point P, or you can think of it as vector P because one side's the origin. If it's compressed, then there's a force at the end kind of facing out, away from the spring. As I move that out and I stretch it, now there's a force coming towards me. So the change in force for a change in position is simply minus k, that spring constant. Okay. Not surprisingly, if the force is minus k times p, well, the derivative with respect to p is just minus k. Standard calculus. Okay. Well, that's only half the equation. Now, consider if I move that endpoint sort of up or down. If my spring is at its rest length, and I grab this other point, and if I move it up or down, well, there's no force and there's no change in force, because for a small change up or down. But the story changes. If my spring is now stretched out, and I'm holding it up here, there's a force kind of coming down towards me from that endpoint. I move my arm down, and now there's a force coming up towards me. So there's a change in force, from this to this, right? So the change is up. But if it was compressed, now I've got this force pointing up. And as I lower the endpoint, now I've got a force pointing down. So my change in force for a change in position, anything orthogonal to the spring direction, now depends on where we are relative to the rest length, r, which is shown in the bottom right there. So for somebody, if they actually went off and they solved all that calculus and came back, they would have come back with this, right? That's what the calculus would have given you. But hopefully, if you follow the geometric intuition and remembered what I talked about at the very beginning with those outer products, this should look obvious because it's simply minus k times that first thing in the brackets there. That's p outer product p divided by p, which is essentially a unit length vector along that direction, outer product with itself. Okay, and that describes this motion, and then the perpendicular motion, simply I minus that for the other term, right? So cool, now you understand what a Jacobian is, okay? The spring equation is probably the easiest difference equation, so this is probably the easiest example for trying to learn what a Jacobian is that you can think of. Now you do the same thing to get change in force for change in velocity, because that's the other, some more derivatives you need. And then you have all these things, and you can put them in the linear system. Now, I don't have time to go into all the algebra and all the details of it, but essentially it's one of those things where you've got one of those big matrices, AX equals B, but X, the unknown, is now delta V. And A, this matrix, is sort of identity minus that term and so on, and B is the other vector. And it's a little more tricky because, okay, it's not just one 3D vector, but your velocity state and your position state are basically this concatenation of all the points in your spring mesh. And this A matrix becomes this big sparse linear system and stuff. All that stuff's, there's sources I can point you to later that describe it all. But I just kind of want to get some of this geometric intuition so you can kind of see how these things work. Okay, so I'm going to illustrate what that can look like at runtime. First, we'll see what the weak springs look like with that forward Euler update. And you see, oh, okay, this is kind of jello-y type behavior. Maybe you could do some ocean waves with this, but it's not real cloth. If you want something to touch and feel like real cloth stuff, you got to use those stiffer springs if you're using the spring-based approach. So here, there's the underlying spring network that you would have, and yeah, okay, you already saw this kind of stuff with the kinetic approach. Kinematic approach. What's the advantage of the implicit integration? Well, here it is. It's when you have these things under stress, right? There's no jitter, no billowing, no energy leaking the system. In fact, when you pull back a slingshot, because you're actually calculating the forces on all these things. So if you put a projectile there, you would know how much force to apply to it so you could launch it, right? It's all sort of force correct. And here's examples of sort of 3D objects kind of connected with a bunch of stiff springs, so on. All right. Okay. Now, that was kind of a big whirlwind of topics, and we started off looking at some basic stuff, how 4 planes come together to meet, building that roof or so on. And we looked at sort of solids and motion and all those kind of things. The main objective here was to try to get people to, first of all, to think of their meshes as not just a bag of triangles, but once you start thinking of a mesh as a solid, and you can have this tetrahedral decomposition or breaking stuff into convex meshes for collision detection. You have this more intuitive, powerful understanding of your geometry. And furthermore, we sort of looked at things in motion, and a lot of people with graphics, you get this fairly good understanding of your basic linear algebra. But when you start exploring some of the physics space and geometry space, you step a little bit beyond some of that math and learning the value of things like outer product and Jacobians and all that sort of thing. And that can open the door to new and interesting, fun things you can do in your game experiences. Okay, so now admittedly that was probably quite a lot for some people to digest, and you might have questions and you might not think of them right away. You might think of them like an hour after you leave here. I'll be around all week, so feel free to flag me down. Just look for the bodybuilder in the crowd. That's me, and we can have coffee and I'll explain things further. In the meantime, if there's any questions that someone has right now, I think we might have a few minutes left to answer. Yeah, got a couple minutes. If someone has a burning question.
I had a non-math related question, which is just what kind of input were you using for those hand gesture demos?
It's like a depth camera based thing. So,
but was it a Connect or a Leap?
Well, in this case, I was actually using a time of flight camera. So what I do I just got my paper published, and a coworker demoed this at i3D last week, a demo poster session. We take the depth, we have a sort of a model of the hand, and then we take the depth data, and we want to fit that model to the depth data. I mean, there's a lot of people who have been trying to solve this problem. I'm sort of like a math 3D physics guy, and I was tasked with assume that I already have this and then build cool experiences and interactions. I'm like, but I need software to track the hand, so I had to like build it because nobody had it. So yeah, I took the depth data, and then I basically got like a rigid body model of the hand and all constructed. And I've got I'll try to be quick. The constraints. You'll learn about this more. You should go to the physics class, because it's really just an extension of like a physics engine. You have all these connections, that are constraints on the joints. You have collision constraints, and then all those little depth values are like little magnets or something, and you just kind of like pull on the surface. There's a few things you want to do. You make them a little weaker because you might mismatch, points to where they lie on the surface, and it relies a little bit on temporal coherence because, if you're starting from a bad frame, it's not going to work. But you kind of need to do that anyway because the depth data is pretty bad. Right, like for the speed and fidelity, because there's can be depth noise and occlusions and all that stuff. So you really kind of need to take advantage of temporal coherence anyway in the solution. But yeah, we can talk about that online. I can show you. I got like a camera here if you're interested. Yeah, but yeah, that's not really related to this talk. But sorry. Any other questions? Sure.
Hey, thanks for that. Touching that last part with like the spring network, and when you do basically integration of like within that time step, do you have to take into account all the like the springs next to your current? Basically, if you have a mass node, basically. With springs,
sure.
You have mass nodes, and they are interconnected with springs.
Yeah.
So basically, all the nodes next to your current node, they kind of have to affect the position or the next position of the node. Do you have to cache all those, like the state of all those nodes that affect your current?
Yeah.
Do I understand?
Yeah. So
I'm having problems expressing myself.
Yeah. So when you're solving any sort of these systems, like even a general rigid body system, you have to solve a lot of these equations simultaneously.
Yeah.
And then with the implicit integration, it's even worse because you're sort of solving kind of future like velocity and position kind of simultaneously as well. So it does get very tricky because everything connects with everything else, and they have to solve them all together. So you end up you end up sort of adding all these little Jacobians, in that system, and then sort of solving into sort of an answer that will, energy minimizing type of thing. Yeah.
But in the middle, you will then have quite a lot of data, basically, more data than you begin with to kind of.
Yeah, it's still going to be. It's going to be order the size, so it's going to be. The topology, the connections of each point, that's like every point can be connected to 12, say, neighbors. And so you're going to have an amount of data to process, like your math equations are going to have that much stuff in them. So it's going to be like, over 10 times the number of points in your matrix, or in your mesh, right? And it's in 3D, so these are, and with position and velocity and other things going on. So yeah, there's a bigger data footprint. Yeah, certainly the kinematic approach, they have a very small data footprint. It's very, it's one of what helps make them more efficient is that makes it cache efficient as well too, because they have a much smaller data footprint. Yeah, no, you're absolutely right. There's a huge data footprint cost as well.
Specifically, I'm just trying to create this really flowy water surface and trying to get away with like. As little problem, like.
Yeah, water you can start out with like the forward Euler systems, because you get sort of that nice wavy behavior, and that's a good place to start. And then for the implicit type things, there is a damping to it that just is natural with the integration. So like the cloth will sort of settle, and it's sometimes you have to do things to kind of create that life back into objects, because even without adding damping terms, it will dampen itself. Which is something that can happen.
Yeah, well, yeah. I've been using the data from the previous step to integrate within the integrations, and I've been getting away with it. For some reason, it works. Maybe my coefficients are low enough for it to work, but
Yeah,
I was
well,
just
yeah. If the
wondering,
coefficient is
I'm
low enough,
probably
yeah, the
getting
forward
into a lot
Euler
of
is
trouble
using.
if I just ignore about this.
Yeah.
Okay, thank you.
Yeah. No
Thanks.
problem. Okay. Oh, sorry. One more.
So a lot of this is actually really new to me, but also seemed really interesting. So for actually trying to like understand the concepts more in detail and really like get it down, would you recommend more like just jumping in and trying to write tech demos that kind of follow this, or would you
Absolutely.
like books? Or?
Absolutely. Even if you're using, you know, at work, if you're using like an off-the-shelf physics engine or something, it's nice to, you know, write your own code of the same thing. Like when I used to work at AGEA on the PhysX SDK and stuff, one of the things that helped me be of benefit to my employer was the fact that I had done a lot of that kind of stuff on my own in the past before, like similar things. Maybe not to the same extent because it's quite a large engine. So yeah, I would encourage anybody, like, you know, try writing a GJK algorithm or a, you know, a little solver for springs, you know, and constantly challenge yourself, because then, you know, even if at work you're using off-the-shelf systems, I mean, you'll understand those systems and the issues involved with them, right? Like that famous force, the mass ratio issue with rigid body ragdolls and stuff, right? Like, what is that? If you've ever kind of tinkered with the equations, it's like, oh, you got it. And then you'll be the guy in the room that, you know, everyone's saying, we can't ship our game because it's broken, and you'll just know, right? So yeah, I would totally encourage that. It's like, you know, it's the same thing as like if you take a math course without ever solving any of the exercises at the end of each chapter, you're not really going to learn the math as well. So that's my personal opinion, but yeah, definitely tinkering is always worthwhile. But you have to balance it out because, you know, you want to get paid, and, you know, you can't spend all your time sort of, you know, reinventing the wheel and stuff. So yeah, I guess I was a little lucky because I'm a little bit older, so like when I was at Bioware in the 90s, none of this stuff existed, and we just had to kind of reinvent, you know, I got the opportunity to kind of implement all this stuff when it was first around. So I know it's a little harder for, you know, new guys coming in the industry because all this stuff's already written. No one's going to pay you to write the stuff that I got paid to write when, you know, 15 years ago. So sorry about that, but, you know, but yeah, definitely, you know, hack on this, on the side. I can't stress enough, that's a very good way to learn.
All right, thank you.
Yeah. All right, well, is that all? I guess thanks, guys, for coming.